So yes, let me know if you guys have any questions. Sorry for the typo there for a second. Oh, hey, Isaac. How's it going? Hey, what's up, Santino? Yes, let me know if you guys have any questions about the work or anything. Yeah, if you guys are both doing the work together, like if he's helping you out with doing some of the research or putting some of it together, that's fine. But you just have to kind of specify what he was doing and what you were doing, basically. Yeah, let me know if you guys have any questions about any of the work. There's no quiz this week or anything like that. The notes today might have been kind of tricky, but we'll get some practice on it tomorrow. And then there'll just be like one other assignment this week. So it's not too much stuff going on this week. Yeah, Isaac, that's fine. Just let him know that he'll have to like tell me what he did. So like I just want to know like exactly which research questions he helped you guys out with and stuff like that. So as long as he can let me know, it's totally cool. I know it might be hard for you guys to meet up because of social distancing and stuff like that, but so that's totally fine. If he helps with some of the research questions, he can just let me know which ones they were. Yeah, no problem. Just let me know if you guys have any questions about anything. No, I don't want you to do that. That sounds dangerous. Please don't do that. Yeah, I won't give you any extra credit. You just might cause a fire or hurt yourself, so please don't do that. It sounds like a bad idea. I guess it doesn't hurt to ask, though. Well, there was an extra credit assignment that was up yesterday. It was the Gizmo activity. Yeah, there was an extra credit assignment up yesterday. There'll be some other things here and there. I would just try to focus on anything from Triad 2. So Triad 2 started like in the beginning of March. So anything from Triad 2 up until which was from the beginning of March up until last week. You can turn that in like till this Friday, but everything was due today technically, so it won't affect your progress report. Like it won't make your grade go up on the progress report, but I'll take it by this Friday if you want. So But yeah, there'll be some more extra credit opportunities here and there, but there's definitely an assignment yesterday that was extra credit. You only had to do 3 pages, but if you do more than 3 pages, you can get more extra credit too. All right, sounds good. Nice. Best of luck. Let me know if you have any questions or anything. Or like if you need your password or username for it's a Gizmo activity. So if you forgot, just let me know. So yeah, with Hess's law, you're really just trying to get a chemical equation based on other chemical reaction equations. And each chemical reaction equation, they're typically synthesis reactions and they have their own enthalpy values, right? So let's say, trying to think of a good example. I'm gonna take a look real quick. Here, I'll try to show you an example. So you have these different step reactions, they call them. I'm going to leave off the phases of matter just to save room. Excuse me. But yeah, like I was saying, they're typically synthesis reactions, so you only have one product. And those one products that you have are going to be something in the main reaction you're trying to build. So let me just write this down. -393 kilojoules. And then all right, so now it matters which phase of matter these things are, but I'm not going to put them down just because I don't have enough room on here horizontally. But just take my word for it that on these equations, it's the correct states of matter we're looking for. So let me show you. So I'm trying to get this reaction down here. This is my target reaction I'm trying to build based on these 3 reactions, which are all synthesis reactions. So the first one's the synthesis of methane, which is up here. The next one is the synthesis of carbon dioxide, which has enthalpy of -393. So they all have their own enthalpy values. And then for the synthesis of water, we have an enthalpy of -484. So I'm just trying to rearrange these things in order to build this. All right, so you're constantly looking at the target equation. This is what you want to create. So first of all, I want 1 mole of methane, CH4, on the left. So 1 mole of it on the left. So just look around for methane. There's none in the bottom one, no methane there. There's no methane here, but there's a methane here, right? I need 1 mole of it on the left side, and I have 1 mole of it, but it's on the right side. Yeah, the stuff on top would be like given. So the problem always looks kind of long, like you have a bunch of equations in the problem. So we'll do some practice tomorrow on Canvas, and the questions are going to be kind of long looking. There's like 4 questions, but you only have to do 2 of them, so you can choose whichever 2. But yeah, these would be given. So you want 1 mole of methane on the left. You only have 1 mole of methane on the first one, and it's on the right. So it's the correct number, but it's on the wrong side. So what you want to do to switch the reactants and products is multiply this by a negative. So if you multiply it by a negative, then it'll switch the reactants and products. So I'm just going to do that real quick. I'm just going to switch them. Right, so we have CHF goes to... Oh man, I can't remember what the other ones were. 2H2 and C. Okay. 2H2 and C goes to C plus 2H2. But I multiplied it by a negative, so now my enthalpy is positive. All right, so I'll show you what I did. So let me make it look a little bit better. I multiplied it by a negative, so now my reactants and products are switched. Now methane's on the left, and the carbon and the hydrogen are on the right. It's the same number, but now it's positive because it was negative before, but since I multiplied it by a negative, now it's just positive. All right, so far so good. We have methane on the left side, and we have 1 mole of it. That's so far so good. I want 2 moles of oxygen. So when it's the same substance on the same side of the equation, they add together. So it's the same substance, it's oxygen, O2, and then this is another O2, and they're both reactants, which is where I want them to be, so they're going to add together. So 1 plus 1 is 2. So that's good. I don't even have to do anything for the oxygen. So I already have my 2 moles of oxygen. It might not look like it right away because there's no 2 here, but I have 1 mole of oxygen here and 1 mole of oxygen there. They're on the same side, the left side, and I want them to be on the left. So they're going to add together 1 plus 1. So that's how we get that. All right. We might be almost done here, actually. Yeah. I want 1 mole of carbon dioxide on the right. There's no carbon dioxide here at all. We have carbon dioxide here. There's none here. So we only have carbon dioxide on the second equation. We want 1 mole of it on the right, and we have 1 mole of it on the right. So we're good to go. We don't really have to do anything for that. So that worked out pretty nicely. You want 2 moles of water on the right. There's no water here. There's no water there. But we have water here, right? It's on the right side. It's on the product side where we want it to be. And it's 2 moles, which is what we want. We want 2 moles, and we have 2 moles there on the right. So we already made this equation, right? Now, it looks like we have some extra stuff here, but they'll probably cancel out. Like, for example, we see these 2 H2s. There's 2 H2 here and 2 H2 there. We don't want H2 anywhere here, right? I don't have H2. I have water and I have methane, but I don't have like H2 by itself. So if it's the same substance on opposite sides, like I have 2 H2 here on the product and 2 H2 here on the reactants, they subtract. And since this is 2 and this is 2, it's 2 minus 2. So they basically just cancel out, right? So this is going to cancel out with this guy up here. So they both cancel out with each other. All right. And then we have some other extra stuff here too, because I have no carbon by itself. I have methane and I have carbon dioxide. So 1 mole of carbon's on the left here and 1 mole of carbon is on the right here. They're on opposite sides, so they're going to subtract 1 minus 1. So yeah, if the moles are different, that's a good question. So in this case, they're the same, right? It's 1 and 1, so they just cancel out. Let's say it wasn't. Let's say it was 2, which it wouldn't be because that would throw off the balance of this. It wouldn't balance correctly, right? But let's say, just for the sake of your question, we have 2 moles of carbon here on the left and 1 mole of carbon here on the right. So it's the same substance. It's carbon and carbon, same substance, and they're on opposite sides. So it's going to subtract still, but just always, subtract the bigger number minus the smaller number. So we're going to do 2 minus 1. So if this were to happen, if there was a 2 here and just a 1 of carbon up here, it would be 2 minus 1. So this carbon would go away, and then this one would just become a 1. You just take the 2 off of here and just get rid of that carbon. So it'd be like 2 minus 1. This carbon goes away, and this carbon over here just becomes a 1 instead of a 2. Right? But in this case, we have 1 and 1, so just 1 minus 1, so they just cancel. Right? But if you have different numbers of moles, like 5 and 2, just do the bigger number minus the smaller number. So if I had 5 on this part and 2 over there, the 2 would go away, and the 5 would become a 3. Right? So it's kind of like that. So now we're all good to go. We have everything here. So usually you have to change these numbers if you have to multiply it by something. Like if I wanted, if I wanted like 4 oxygens instead, maybe I needed to multiply this by like a 3 or something, then that would change this number. Kind of like how the only thing I did here was I multiplied the first one by a -1, which made this positive instead of negative. So your final answer is just adding all these things up together. So it's going to be -484 plus -393 plus 74.8. So it's going to be some big negative number. That's like your final answer. Yeah, so that was a relatively more simple example, but there can be more complicated examples. If you want, we can go through another one. I think from now on, I'm going to probably start posting these live streams on Canvas too. I feel like I don't know why I haven't been doing that. That'd be a good idea. But yeah, if you want to, we can go through another example or anything if you'd like. So yeah, enthalpy is just the measurement of the internal energy. So for those chemical reactions, a lot of them are negative, meaning that more energy was being released to form products than was being absorbed to form to break apart the reactants. Are you asking like what the final answer was? Because we can look at that. The final answer would have just been -484 kilojoules minus 393.5 kilojoules plus 74.8 kilojoules. Yeah, because the final answer is always going to be a numerical answer for the total enthalpy. So minus 393.5 plus 74.8. So yeah, it's a big negative number, negative 802.7 kilojoules. So yeah, because the only one we changed was this one. It was originally negative, and it became positive because we had to multiply it by a negative number. So when you add them all together, you get negative 805.7 kilojoules, and that makes sense because it was a combustion reaction, which combustion reactions always release heat. So negative enthalpy because enthalpy is internal energy for the chemical reaction that we're looking at. So, like I said, if it's negative, that's more energy being released as a product. And if it's positive, that's more energy being absorbed on the reactants. Energy is not created or destroyed, so it's conserved no matter what. It's the same on both sides. But if it's negative, there's more energy being released as the products form in comparison to the energy being absorbed to break apart the reactants. Because again, to do a chemical reaction to go from reactants to products, the reactants have to break apart their bonds, which absorbs energy. And the products, to form new bonds, they have to release energy. So if it's negative like this, there's a lot more of energy being released in the formation of the products than there was needed to absorb into the reactants breaking apart their bonds. I'm not sure if that answered your question, though. Yeah, so the final answer is going to be a numerical answer. So sometimes when they get more complicated, like if you have to multiply a reaction by a number, it'll change that value a lot more. In the end, you just have to put them all together. Oh yeah, the definition is just the internal energy of a substance. So it's the energy, like if you're talking about enthalpy for a reaction, like the one for methane that we had. It's 2H2. Yeah, it's the internal energy of a substance. Technically, that's a limited definition. It's the internal energy plus the product of the pressure and volume that that substance takes up. But we're not going to really focus on that part of it. We're just kind of focusing on the internal energy of the substance itself. So that's due to the substance's chemical bonds, especially. So one of the reactions we had, I erased it earlier, but I'll write it down again, was this one. So this is one of the given reactions on the top of the problem for the synthesis of methane. So for the synthesis of methane here, I get negative 74.8 kilojoules of enthalpy. So again, it's in joules or kilojoules. So enthalpy is another form of energy, really, because energy is measured in joules. So that's why it gets kind of tricky, because energy is like the big umbrella general term. And, work is measured in joules too, and heat's measured in joules, which, like the question we answered yesterday, it's just the transfer of energy from hotter objects to cooler objects. And enthalpy is also a form of energy. It's just that internal energy that's within the substance due to its chemical bonds. So for the synthesis or production of methane here, you get negative enthalpy. So that's exothermic. So that means there's more energy being released to form CH4, because when bonds form, they release energy. So more energy is being released to form CH4 than was necessary to be absorbed to break apart these chemical bonds for the reactants. It's just carbon by itself, so really it's just the H2 that has to break apart its bonds. Yeah, it's pronounced the exact same. Yeah, joules. But yeah, so if it's negative, it's exothermic. If it's positive, it's endothermic. But it's just the internal energy of the substance, really, due to its chemical bonds. Because there's energy within the bonds themselves. A chemical reaction happening, basically. So it's also energy, right? It's another form of energy. Okay, cool. Yeah, it's just another form of energy. So its equation is this. Right, so Gibbs free energy is the energy basically that relates to how spontaneous a reaction will happen or a reaction will occur. So it relates to enthalpy. So it relates to enthalpy as well as the entropy, which is S, the entropy as well. And we know, well, we haven't looked at the notes for this yet. They'll come later this week, but I think I was talking to you in a different live stream that entropy is basically the measurement of disorder or possible combinations or possible states that a system could be in. And T is the temperature. So if the entropy is really big, if there's lots of possible different combinations for a reaction to occur, based on where these molecules and compounds are at, we're going to get more likelihood that this is going to happen. So the spontaneity, Gibbs free energy basically just tells us how likely a chemical reaction is going to happen. So if the Gibbs free energy is negative, if it's something that's negative, then it's going to be more spontaneous. And the reason why it has to be negative is because the entropy here, if it's going to increase, then that's going to be positive, right? Because things that are more likely to happen are in relationship to an increase in disorder or an increase in entropy, right? Like, for example, I know it's not really a chemical reaction, it's really a physical reaction, but like an egg, right? If you have a complete solid unbroken egg, that's very orderly. There's only one state that this can be unbroken. But for the egg to be smashed on the ground, there's so many numerous different possible combinations and variations that you can break an egg. You can drop it, you can throw it on the ground, you can smash it with your foot. But even then, there's so many different ways you can do each of those things. You can smash it and throw it at different speeds. You can squish part of it or half of it or a quarter of it. Like, there's so many different possible ways that it can be broken, but only one way for the egg to be unbroken and complete. So entropy is an increase in those possibilities, those possible variations or disorder, right? We call it disorder just because there's so many different ways that you can get to those states, right? So an increase in entropy or an increase in disorder means that something's more spontaneous. More spontaneous things that happen by themselves are when there's more possible ways that you can get to that state. There's more disorder in the system. So an increase in entropy, if this is really big, and it's at the end of the subtraction problem here, that means Gibbs is going to be negative. So we know that it's going to be more spontaneous if entropy is positive. So that means it's going to be more spontaneous if Gibbs is negative. So how can we make Gibbs more negative is if enthalpy is also negative. So if the enthalpy is also negative and the entropy is positive, then Gibbs is going to be more negative as well. So exothermic reactions, enthalpies that are negative, kind of like the example we just saw, it was negative for a combustion reaction, those are more spontaneous, more likely to happen, right? Because with combustion reactions, that's when they release carbon dioxide and oxygen, as well as heat, and there's so many different ways that things could combust or blow up, right? There's so many different ways they can release this huge amount of heat, but we have an increase in possible variations to get there, an increase in entropy. It's going to be more spontaneous. So that means it's going to be more negative Gibbs. So if the Gibbs free energy is negative, it's going to be more spontaneous, more likely to happen. If it's positive, it's going to be less likely to happen. Not impossible, but in some cases almost impossible, like a super tiny, tiny percentage. Right. It's kind of like, having it's like having a big bowl of gumballs. If you have all these different colors like red, green, orange, yellow, blue, whatever, and people bump into the jar as they're walking in and out of the restaurant, right? If they keep bumping into it, that's spontaneously going to shake it up, right? So as it spontaneously shakes itself up, it's more likely to be in disorder. It's more likely to be random, like the red over here, maybe the blue over there, and the white and the green, like all kind of mixed up. It's almost impossible for it to look like this. All the red in a row, all the orange in a row, all the yellow in a row, all the green in a row, like super like ordered and evened out like that. That's a very ordered state. There's only one way you can, or not necessarily one way, but there's very fewer ways to get the gumballs to look like that in layers. But there's so many different ways the gumballs could be mixed up and not in layers, right? Because if you put like a jar of gumballs at the opening of a restaurant and people are walking by it and bumping into it, It's more spontaneously going to be jumbled up and mixed up. It's going to be a super tiny likelihood that it's going to be like this, right? So something like this, all these gumballs ordered and all lined up according to their color, you kind of have to do that yourself. You have to interfere with the system and actually use your hands and do that. It's not impossible to get this by bumping into it. It's just extremely unlikely. So something like this would be negative entropy. This all nice and ordered, that's negative entropy. That's not spontaneous. Spontaneous things are positive entropy. Things like this, a positive entropy. So if my delta S, my entropy is positive here, it's going to make Gibbs negative because it's at the end of the subtraction problem, right? If this number gets really, really big, then this is going to more likely be something negative. So if this is going to be negative and that's going to correspond to a spontaneous reaction, the negative enthalpy will help us get there as well. So if enthalpy is negative and entropy is positive, we're going to have negative Gibbs, and that just means it's a more spontaneous chemical reaction. So it's kind of weird because it's best to explain with these physical reaction examples. These aren't chemical reactions, breaking an egg, mixing up gumballs. They're all physical reactions, right? Nothing is chemically recombining here. But it's kind of the best way to put it as like an analogy to what's happening with chemical reactions. So yeah, we'll take notes on this stuff on Friday. It's kind of like what we're going to end this unit with is Gibbs free energy. So we're going to end the unit on Friday pretty much. But yeah, hopefully it kind of made a little bit of sense. You're not going to have to do any math with this at all. You just have to know for spontaneous, it looks like this. For non-spontaneous, it's the opposite. This would be negative, that would be positive, and that would be positive. So yeah, I just think some of those examples that are physical reactions are a little bit easier to illustrate the point. Yeah, let me know if you have any other questions or anything. Well, temperature is there because entropy is joules per coulomb, or no, Kelvin, not coulomb. Coulomb? I'm Kelvin. Yeah, sorry, I'm getting my words all mixed up. It's joules per Kelvin. I hope I wasn't saying coulomb in the other videos now. That's a unit of charge. Yeah, so entropy is joules per Kelvin. So temperature is measured in Kelvin, so we have it multiplied here so that way the Kelvin units can cancel out and we can get everything in joules because Gibbs is measured in joules, enthalpy is measured in joules. So temperature is here as basically a constant of the system, something that's a control. So the temperature is not going to change, right? That's why everything else has the delta sign in front of it because they're susceptible to change. You can change the enthalpy, you can change the entropy, and that will, of course, change this, which is dependent on both of them. It'll change the Gibbs. But the temperature itself is a constant of the system, so that's not going to change. Yeah, so that's just like one control we have, basically. And it allows the units to cancel out because entropy is joules per Kelvin and temperature is Kelvin, so that way the K's can cancel out and just give you joules as well. Yeah, that'll be like the last thing we look at for this unit. It'll be notes on Friday. Oh, yeah, I mean, you can't go to a barber right now, so that's why I haven't gotten a haircut. Like I would never like have myself do it. That's probably a difficult idea. At least you, I guess, won't have to show it off for a while. You can stay indoors and no one will have to look at it. Yeah, that's true. Yeah, let me know if you guys have any other questions about anything though. Yeah, some of this stuff gets kind of conceptual and tricky, especially entropy and enthalpy and Gibbs and how they all interact. It gets kind of tricky after a while, but hopefully some of the other videos are also helping too. Are you talking about like ones that you already took that you want to just retake again from like when we were physically in class? Because I got your tests and your quizzes this morning. I already graded them, so I put those in already. So yeah, the test and quizzes you sent me this morning or last night or something, I put those in the grade book already. Yeah, so I mean, the test retake policy is pretty much the same. So like, if you want to retake any of those, if you do worse the second time, basically I just keep the original score, and if you do better the second time, then I basically take like the average of both of them. Yeah, no problem. Yeah, so if you do worse the second time, I just take the original score. If you better the second time, I will just take the average of both of them. But yeah, they definitely were able to bring her grade up quite a bit more because they were a good percentage. They probably went up by like 15% or something. Yeah, I'm not sure. They're kind of talking about that for next year, like rumors about how things would go, because even when we're if we're able to go back to school in person next year, we're still gonna have to social distance to some extent. So I have no idea really, but some people are just kind of throwing out ideas as like rumors, like maybe we would only see half of the students like every other day or something like that. Or are you asking like which ones you got wrong? Is that what you're asking? But yeah, we don't know for sure what's gonna happen as far as like going to school again next year. Yeah, for those, I mean, you did pretty well on the intermolecular force and solid type quiz. For the stoichiometry quiz and the stoichiometry test, it was really just the problems that were like stoichiometry calculations themselves. So the problems they did like stoichiometry calculations on, that's where something got wrong. That's where something got messed up, basically. No, actually, yeah, we're not going back at all this year. In the whole state of California, we're basically just doing the rest of the year online, pretty much. Yeah. Yeah, so like, you balance things okay, Jacob, and you got the other stuff fine. It was just like the stoichiometric calculations themselves. So maybe something with the calculator, maybe something with the fractions, maybe using the mole house. Yeah, so we're not going to be going back at all this year. It's just going to be all online. So definitely something to get used to. I feel like I've gotten used to it pretty well already, but this makes things difficult. Yeah, no problem. But yeah, let me know if you guys have any other questions at all. Yeah, that's still up in the air. I'm honestly not sure. I gotta talk to the other people in my department about that. Because it's gonna be kind of weird doing finals virtually. So I'm not sure yet. I still got to get back to you guys about that. I'm gonna talk to my department chair, maybe some other science teachers, and how they're gonna do it. Some science teachers I think aren't even gonna do it at all, but I'm not sure what the majority wants to do. So yeah, I'll have to get back to you guys. Yeah, let me know if you guys have any other questions or anything. Oh yeah, probably. Yeah, proteins are really long, complicated compounds. Yeah, so it's something really long, I'm sure. Yeah, I can't even find it. Yeah, let me know if you guys have any other questions or anything. I might end it in just a couple minutes if you guys don't need any other help. I'll try to do another one of these at least on Thursday, maybe tomorrow if I can, but for sure Thursday. Um, there might be some upcoming, but I don't know if they're like that exciting necessarily. There might be some ideas for ones like in the next unit that we're going into, there is one lab that just requires like different types of beans, like black beans, kidney beans, things like that, lima beans. Um, and you could definitely try that one out, and you don't really need anything virtual for it. I don't know how fun it is necessarily. I mean, you're mostly counting and sorting. It's kind of interesting. I mean, I enjoy it, but I'm not sure how like interesting it might be for anyone else. There might be some other ideas though, but mostly just virtual, to be honest. Yeah, so there might be a few, um, but some of them are not super fun, and other ones might be maybe dangerous. Well, the next unit we're going to be looking at reaction rates and equilibrium. So it's more about chemical reactions and how quickly they occur, basically. But also, we're going to start looking at reactions where the arrow goes both ways. So what that means, and we'll see in the next unit, is that the rate that reactants become products is the same as products becoming reactants. The most simple example for that isn't really a chemical reaction. I mean, yeah, it's really just a physical reaction. Like if you have some water and like it's in a flask that's sealed like this, and you put it out in the sun, right? If you put it out in the sun, the water is going to start to evaporate, and we know that basically at the surface of any liquid, no matter what the temperature is, there's a little bit of evaporation going on at the surface, because you're absorbing the most energy from the outside surroundings at the surface of the liquid. So for water as a liquid, H2O liquid, um, if you leave that sealed container out in the sun and just leave it sealed so the vapor can't leave, you'll start to see in a couple of days it'll look kind of like foggy up here on the empty part. You'll see some like vapor. So that's the H2O gas and the H2O liquid. So something like that, H2O liquid to H2O gas, they're going through a phase change at equal rates. So the liquid H2O is evaporating into steam just as often as the steam is condensing back to liquid. So this double arrow just means, it doesn't mean reactants and products are equal. People get that mixed up. It doesn't mean that. It just means that reactants become products just as often as products go back to reactants. So the exchange rate's the same. That's pretty much what it means. But we're going to look at that in the next unit, as well as equilibrium, which is well, basically that is equilibrium, but we're going to look at factors that affect reaction rates too, things like temperature, pressure, and concentration. What I was just talking about was actually equilibrium. So that's what equilibrium is, an equal exchange rate. But we'll start looking at factors that affect reaction rates too. And then there's one more unit after that, which is just acids and bases, and a little bit more of a review on mixtures and solutions. If we had time, we'd do OChem after that, but I doubt we'll have time for that. Yeah, but I mean, with those, they typically just go one way, right? Photosynthesis just goes one way, and respiration just goes one way. It just happens in different organisms, right? So photosynthesis is for plants, cellular respiration is for us mammals and things like that. But for equilibrium, it has to be going both ways simultaneously. Yeah, we'll see there's some examples out there with like hydrochloric acid reacting in water or dissolving in water. Yeah, there's a few different examples we'll look at with equilibrium. But yeah, it just means the exchange rate's the same. It doesn't mean you have the same amount of reactants as products, like those aren't equal. It just means that the amount going back and forth is the same. But the individual populations of reactants and products might be still higher in concentration on one side than the other. Yeah, I'll probably get going in a minute. I'm just gonna organize some things on Canvas for a little bit. But I'll try to do one of these tomorrow too. I'll for sure do one on Thursday, but I'll try to do one tomorrow too. Yeah, I'll probably see you later then if you don't have any other questions. I'm gonna have to take off at the moment though. But yeah, we'll have some more practice with Hess's Law tomorrow, and I'll try to do one of these tomorrow in case you guys have any questions about it. All right, take it easy. See you guys later. Bye.
It's calling